Millions of dollars of raw materials and thousands of labor hours snap into motion on factory floors every day, all driven by an attempt to anticipate future consumer demand. To prevent operational chaos, corporations organize this massive physical effort through a strict hierarchy of business plans and short-term budgets. This flowchart maps the corporation's budgetary structure. Notice this bureaucracy cascades from a single point, the sales budget. Projected sales dictate the production budget, which determines the direct materials, labor, and overhead required, flowing down into the cost of goods sold. If that initial sales projection is based on flawed guesswork, every subsequent calculation is compromised, turning the final master budget into an elaborate fiction. Managers often rely on qualitative forecasting, their own experience and intuition, to guess that top-line number. But intuition scales poorly. For objective reliability, organizations require quantitative forecasting using mathematical models. These models organize historical data in two main ways: time series analysis, which looks at performance over successive periods, and causal relationship forecasting, which compares performance against specific environmental factors. The first step in extracting a mathematical trend from this history is plotting past operational data on a Cartesian plane. The horizontal x-axis maps the independent variable, the causal factor or time period, while the vertical y-axis tracks the dependent variable, like sales or costs. Managerial accountants look at these scattered data clusters to solve a very specific problem, isolating the fixed baseline costs from the variable costs that fluctuate with activity. To build a budget that actually works, analysts have to cut through the noise of these scattered plots and find a reliable, predictive mathematical equation. Before deriving an equation, we need to know if a relationship even exists. Correlation analysis serves as the statistical foundation for any quantitative forecast. It measures the strength of the linear relationship between two variables, summarizing how tightly the data clusters along a path into a single metric called the coefficient of correlation, or R. The value of R is strictly bounded. It ranges from a perfect direct relationship at +1 to a perfect inverse relationship at -1. If the points form a random, formless cloud, the R value drops to 0. But an R of 0 contains a statistical trap. If the data perfectly forms a symmetrical U-shape, the R value is still 0. The variables in that U-shape have a highly structured, predictable relationship, but because correlation only measures straight lines, it fails to detect the pattern. Even when correlation does confirm a strong linear relationship, it only diagnoses the strength. It does not provide the actual math. Knowing a trend exists is an incomplete step. We need a mechanism to calculate its exact trajectory for the forecast. That mechanism is simple regression analysis, the process of deriving the single straight line that best describes the scattered data. This data table tracks observations from a firm attempting to forecast millions in annual sales based solely on their advertising expenditures. Looking down at figure 12-5, we see those specific observations mapped as points, with a single linear trajectory slicing through them. The placement of this line is calculated using the least squares method. It is positioned exactly where the total mathematical error is minimized. We measure that error by looking at the vertical distance between each actual historical data point and the predictive model's line. By applying calculus, the method squares those vertical distances, punishing severe outliers heavily, and locks the line at the exact angle where the total area of those squares is minimized. This yields the algebraic formula for a straight line, y equals a plus bx. Regression strips human bias from the forecast, replacing it with a mathematical engine strictly designed to find the path of least error. For cost accountants setting up a flexible budget, this equation is practically required. It mathematically dissects mixed costs into their separate fixed and variable components. This dataset from Wilkins Company shows 12 months of maintenance costs paired with hours of activity. Instead of guessing the breakdown, the regression output in the left column gives us the exact variables for our equation. The y-intercept, represented by A, is $684.65. That is the fixed portion of the monthly maintenance cost. The slope, B, is $7.28. This represents the variable rate applied to every single hour of activity. We have an exact equation, but how can a financial analyst prove it is accurate enough to serve as the foundation of the master budget? We look at the R-squared value, known as the coefficient of determination, to measure the exact goodness of fit. This metric defines the proportion of total variation in the dependent variable that is mathematically explained by the independent variable. Here, 99.7% of the cost fluctuation is explained by activity hours, leaving almost no unexplained noise. A near-perfect fit provides financial leadership the mathematical confidence required to finalize and approve the budget. Yet relying blindly on a 99% R-squared value can still trigger a corporate disaster if the analyst ignores the structural boundaries of the model. The most common forecasting trap is treating the regression line as if the linear relationship remains valid infinitely in all directions. The model is only accurate within the relevant range, operational limits where cost rates remain constant. Projecting the dashed line backward until it crosses zero breaks the math, yielding absurdities like negative fixed costs. Regression also relies on a core economic concept called the ceteris paribus assumption, meaning all else being equal. The method strictly assumes that the business environment, pricing structures, and cost patterns from the historical data will remain completely unchanged in the future. The data must also maintain homoscedasticity, meaning the variance of points around the regression line remains relatively constant and doesn't fan out unpredictably over time. A predictive model is a rigid mathematical mirror of past conditions. If the underlying environment shifts, the mirror shatters. Before calculating, analysts must determine which independent variables actually drive the business, as seen in this automotive parts question. The text asks whether sales depend on broad industry trends or localized automobile sales. Testing this avoids building an irrelevant model. In complex markets, tying a forecast to a single variable is usually unrealistic. Firms rely on multiple regression to identify and correctly weight several independent factors at once. But regardless of how many variables are used, the ultimate rule of quantitative analysis remains. Regression only tracks mathematical covariance. It never proves actual causality. Take a car wash. Sales volume and sunny weather are heavily correlated mathematically, but operating a car wash doesn't cause the sun to shine. An algorithm only sees numbers moving together. It cannot distinguish between a coincidence and a true driving force. While regression provides the mathematical rigor to strip away statistical noise, human intellect remains the final, indispensable safeguard for the master budget.